So far, three discrete distributions have been introduced. The first was the Bernoulli distribution, which had the outcomes 0 and 1. And that Bernoulli distribution led to the second distribution, which was the binomial distribution. Finally, we just finished the geometric distribution, and the geometric distribution with a small g models the number of failures before the first success in repeated independent Bernoulli trials, each with a probability of success p. So now we're introducing a fourth discrete probability distribution which comes up in applications quite often, and it is the negative binomial distribution. The negative binomial distribution models the number of failures before the rth success in repeated independent Bernoulli trials, each with probability of success p. So this sounds a lot like the geometric distribution, but instead of the number of failures before the first success, now that's being generalized to the number of failures before the rth success. Once again, the support will begin at 0 and go to infinity, because you could have 0 failures before the rth success, or 1 failure before the rth success, etc. Now at this point we're going to try to derive the probability mass function for the negative binomial distribution, and here is one way of proceeding. The probability of r successes and x failures in a specified order, and for example I have failure, failure, success, failure, 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 success, success. This particular string right here, if you wanted the probability of getting this string in a specific order, and notice that we are waiting for the third success here. 1, 2, 3. And notice in addition, in this particular string, we had 5 failures, 1, 2, 3, 4, 5, before we got our third success. In general, that will be p to the r, and that's the probability of the rth successes, and then 1 minus p to the x, that right there is the probability of the x failures that occurred before that rth success. But we aren't looking for them in a specific order, so we need one more term. Let me go ahead and put a couple blanks in here. If this is our sequences of trials, and I will not lay out failures and successes in this case, all I'm going to do is indicate that I know that this last one is a success, and I also know that it is the rth success. Well, if that is the case, what can you tell me about the composition of all of these positions right here? Well, we know that if this is the rth success, then we must have r minus 1 successes back here. Okay, and that corresponds to a total of r successes on all the trials. But in addition, we have to have x failures that occur back here. Now, that means that the number of trials that occurred before this rth success was x plus r minus 1. So there is the top of the number of combinations. And in those x plus r minus 1, we have to somehow distribute either our r minus 1 successes or our x failures. You could put either one down here, but I'm going to go ahead and put down the r minus 1 successes, and that is the number of different sequences of failures and successes associated with x failures prior to the rth success. Now basically that derivation right there is going to lead us to a definition of the negative binomial random variable, and here it is. A discrete random variable x that has probability mass function f of x is equal to x plus r minus 1 choose r minus 1 times p to the r times 1 minus p to the x for x equals 0, 1, 2, etc. for some positive integer r and some probability of success on each Bernoulli trial that lies between 0 and 1. That is a negative binomial random variable with parameters r and p. Notice this n is lowercase because we're going to have the same problem we had with the geometric distribution, and we're going to have another negative random variable or negative binomial random variable that starts with a capital N. 4 notes. First of all, sometimes the negative binomial distribution is called the Pascal distribution. Not very often. Typically it's known as the negative binomial distribution. The shorthand here is x is distributed as a negative binomial random variable with parameters r and p. The geometric distribution is a special case of the negative binomial distribution when r equals 1. And furthermore, a negative binomial random variable can be thought of as the concatenation of r random experiments associated with the geometric distribution. In other words, when you get to your first success, that's geometric, and then you start the experiment all over and you move forward until you get to your second success, all the way until you get to the rth success. If you want to draw a little diagram that illustrates these last 2 bullet points, here is a geometric random variable with parameter p. I'll put a circle around here, and here is a, I'll have to abbreviate, negative binomial random variables with parameters r and p. So there is that distribution. If you look at a negative binomial distribution and look at the special case associated with r equals 1, that is geometric. On the other hand, if you have a number of geometric random variables, let's call that first geometric p random variable x1, and the next one another geometric p random variable x2, and if these are independent random variables, that'll be defined a little bit later, and you add them up, that's how you go from geometric p random variables to a negative binomial. So that relates the geometric and the negative binomial. One is a special case, the other is known as a convolution in probability, where you're adding up mutually independent and identically distributed geometric random variables.